So, welcome to the first lecture on cryptography and information theoretic security and the one-time pad. So, as always, we want to start with a definition. So, symmetric ciphers. Right, so we want to define a cipher over the triple, which defines the environment over which a cipher is defined, so K, M, and C, right, over a set of all possible keys denoted by the script K or the key space, right, the set of all possible messages and set of all possible ciphertexts, right. So is a pair of efficient, and efficient here is in quotes, algorithms E and D, where the following is true. Right, so the cipher itself is a pair of efficient algorithms where E is the encryption algorithm and D is the decryption algorithm. Right, so efficient here is in quotes because it means different things to different people. If you're more inclined toward theory, efficient means runs in polynomial time and the size of their inputs. If you're more practically inclined, efficient means runs within a certain time period, right? Polynomial time or essentially concrete time constraints. So such that for every message in the message space, right, and for every key in the key space, then it had better be the case that if we essentially encrypt the message with the key K, and then we decrypt using the same key K, then we had better get back the message, the original message that we started with. Right, so this here is what we call the consistency equation, and every cipher must satisfy it in order to be a cipher. So otherwise it's impossible to decrypt. Right, so encryption takes keys and messages and outputs ciphertext, and D takes keys and ciphertext and outputs messages, right? And that's really all cipher is. It's two algorithms, encryption and decryption, E, and D, right? So E is often randomized. Right, so as you are encrypting messages, algorithm E is going to generate random bits for itself, and it's going to use those random bits to actually encrypt the messages that are given to it. And so D is always deterministic. So by this, the decryption algorithm is always deterministic in the sense, given the key and the ciphertext, output is always the same. It doesn't depend on any randomness that is used by the algorithm. So then we get to the topic of the one-time pad. By Vernam in 1917. Right, so this essentially is what's called the first example of essentially a secure cipher, and secure here is in quotes. So the message space for the Vernam cipher, the OTP, is the same as the ciphertext space, which is just essentially the set of all n-bit binary strings, right? All sequences of bits, all 0-1 characters, right? And K is essentially the same thing as the message space, right? So it's going to be this set of all n-bit binary strings, right? And K, key K, is the random bit string that is as long as the message itself. Okay, so the OTP is, the key in the OTP is simply a random bit string, right? And so then we define a ciphertext. So the ciphertext is the result of encrypting a message, message M, with a particular key K, and that is simply the XOR of the two, right? K XOR M, right? Where XOR, of course, means addition modular 2, right? And so just a quick crash course on modular addition modular 2. So the message, right? So if we have a message, we take a message 0 1 1 0 1 1 1, right? So if you take a particular message and you take essentially a particular key K, when I compute the encryption of the message using this key, all you do basically is compute the XOR of the two strings, right? The addition modulo 2 bit by bit, right? So if we have a key 1 0 1 1 0 0 1, right? XOR the 2, then out comes the ciphertext 1 1 0 1 1 1 0, right? And that's it. So then we define decryption as follows: decryption K C is equal to K XOR C, right? To decrypt, basically, all you do is the same thing. To decrypt a ciphertext using a particular key, we XOR the key and the ciphertext again, right? So then we have to verify that this satisfies the consistency requirements, right? So indeed, we see that this is true. So if we encrypt a message using a particular key, and then we decrypt using that same key, we get, if we rewrite this, we get as follows, M, right? Which is the same thing as K XOR K XOR M, right? And because addition is associative, this is the same thing as K XOR K XOR M, right? K XOR K is 0, and 0 XOR anything is simply that thing. So 0 XOR M, right? So if this is 0, then 0 XOR M is going to be M, right? So we had to make sure that if we decrypt a ciphertext that was encrypted using a particular key, we had better get back the message M. So if we look at the encryption of K and M, there we go. All right, so now let's say we're asked a question. So we are given a message M and its OTP encryption C. And now we're asked, can you compute the OTP key from M and C? Right, so in other words, if we're given this pair M and C, can we actually figure out the OTP's key that was used in the creation of C from M? And of course, the answer to this is yes. The key is K equals M XOR C, right? That's it. So the one-time pad, of course, is really, really cool actually from a performance kind of view, because all you're really doing is you're XORing the key in the message, so it's actually a super fast cipher for encryption and decryption, right? So the one-time pad, right? Very fast encryption and decryption, right? So those are some good things about it. But it has, unfortunately, very long keys, right? And it's important to note that they are actually as long as the plain text, right? So that's a huge problem. Because it actually makes it very difficult to use in practice. The keys are as long as the message, but the idea is incredibly useful. So if Alice, so this is the problem. So here's a scenario. If Alice wants to send message M to Bob before she begins even sending the first bit of the message, she has to transmit the key to Bob that's as long as that message. And if Alice has a way of transmitting a key that is secure, that's as long as the message, she might as well just use that same mechanism to also transmit the message itself, right? So that's the problem. So then we have to really ask, what is a good cipher to begin with, right? What makes it secure? Is the OTP, so is the OTP even a good cipher, right? So this is an important question. And so the next lecture we're going to talk about that is Shannon's idea of perfect secrecy. And we'll discuss a little bit more about what it means to actually be a good cipher.